In this video, we will be looking at inverse functions. So an inverse function is a function that reverses or it undoes another function. Mathematically, f and g are called inverse functions if f of g of x is equal to x and g of f of x is equal to x. Inverses are typically notated as f inverse of x. This -1 is saying that it's the inverse. So when I read this out loud, I'm going to read it as f inverse of x, not f to the -1. In these first few examples, we want to determine whether or not these pairs of functions are inverses of each other. The way we're going to check that is we are going to look at the compositions f of g of x and g of f of x, or whatever function names we have. If we get x in both cases, then they are inverses of each other. So first up, we have f of x equals 2x minus 8, and g of x equals x plus 8 over 2. So we will find f of g of x. So that'll be 2 times what g of x is, x plus 8 over 2, minus 8. Well, multiplying by 2 and dividing by 2, those 2's divide out, and I'm left with x plus 8 minus 8, which is x. So that one checks out. We have to check g of f of x as well, too. So I'm going to take my g of x function, which is x plus 8. I need to replace the x with what f of x is. We get 2x minus 8. And then it says add 8 and divide by 2. My 8's cancel out, and 2x divided by 2 is just x. So since f of g of x was equal to x and g of f of x was equal to x, this first pair are indeed inverses. For the second one, we have j of x and k of x. So first we're going to look at j of k of x. That will be 2 times what k of x is, x over 2 minus 4, plus 4. So I need to distribute my 2 through. 2 times x over 2 is x. 2 times -4 is -8. And then we have a plus 4 out back. That simplifies to x minus 4. That is not just x. I need it to be just an x. Therefore, those two are not inverses. It's enough to show just one way it doesn't work. Finally, we have m of x and n of x. We have the square root of x minus 6 and x plus 6 in parentheses squared. So we'll start with m of n of x. So we'll have the square root of, I'm replacing my x with x plus 6 quantity squared, and then we have a minus 6. That x plus 6 in parentheses squared, I'm going to have to FOIL that out. So that's going to be x plus 6 times x plus 6, and then I have a minus 6 out back. So that'll be the square root of x squared plus 6x plus 6x plus 36 minus 6, which is the square root of x squared plus 12x plus 30. Well, I'm trying to get an answer of just x. If I'm taking the square root of something other than x squared, I'm not going to get x. So this is not going to simplify to just x. These two are not inverses. We could try to factor this. If I take my a times my c, 1 times 30, that gives me 30. The different ways to multiply and get 30 would be 1 and 30, 2 and 15, 3 and 10, 5 and 6, and then all the negatives of those. And none of them add up to 12. So this doesn't even factor. So I can't simplify that at all. That is definitely not equal to x. Therefore, that bottom set are not inverses. Next up, we're going to look at the graphs of inverse functions. And this might clue in a few of you who have mentioned the horizontal line test in the past. To determine whether or not a function has an inverse just by looking at the graph, you can use the horizontal line test. And it's just going to be like the vertical line test, but with a horizontal line instead. If the graph of a function is such that no horizontal line would intersect the graph in more than one place, then the function has an inverse. So the darker line, or the darker curve here, is the function f. It is a function because it passes the vertical line test. It has an inverse because it passes the horizontal line test. What's really cool about inverses is that they are symmetric over the line y equals x. The line y equals x is this one. And if you reflect it over, you get the inverse. So we're going to practice with this a little bit. It's kind of fun. Here I have two graphs and I want to graph the inverse. And I'm going to zoom in so we can really see what's going on here. All right, first up, we have this graph and I want to reflect it over the line y equals x. And I'm going to show you a neat little trick. So this point right here that has an open circle on it is located at 0, -1. If I reflect it over this line, it's going to end up right here as an open circle. And the coordinates of that point are -1, 0. Do you notice anything? My x's and y's switched. It was 0, -1, now it's -1, 0. This point here has coordinates of 5, 0. If I reflect it over the line, it's going to end up right here at the coordinate 0, 5. That's kind of cool, isn't it? I kind of think so, but it doesn't take much to get me excited about math. Well, those two are connected with a straight line, so I can connect these with a straight line, and hopefully you can start to see that symmetry. And then this point is at -1, -5. So if I switch that, -5, -1, it's going to be here. This point down here is at -2, -6. If I switch those, -6, -2, that'll be there. And then I just have straight lines connecting everything. So what I have are my original function. It was a function because it passed the vertical line test. It has an inverse because it passes the horizontal line test. And to get what the graph of the inverse looks like, I reflect it over the line. And what was neat about that was our coordinates of our points just flip-flopped. What was an x was now a y. What was a y is now an x. Next up, we have this graph here. Again, I want to reflect it over the line y equals x. And we learned that we can just exchange the x and y coordinate values. So this point here, let's do it in a different color so it'll show up pretty well. This point here has coordinates -2, +4. So I need to go to +4, -2. +4, -2. And that's a closed circle. This point is at 2, 3. So I need to go to 3, 2. Right now I have an open circle at 3, -1. So I need to go to -1, 3 and put an open circle there. And then I have a closed circle at 5, -2. So I need to go to -2, +5 and put a closed circle there. And then I connect the dots in the order that I made them. It probably doesn't look like quite as well of a reflection over that line, but it's hard to picture when you have part of it on one side and part of it on the other. If you just look at that half of the original function, you might be able to see how it mimics that on this side. And then if you look at this side of the original function, you might see how it mimics it on that side as well. So when it comes to graphs, find a few important points. I just looked at where it kept turning, and I used those corner points and plotted those, and then I was able to connect the dots between them. And all we had to do was exchange our x and y values, and that gave us the inverse. That's kind of cool. Now we're going to see if we can find the inverse from a table. So first up, we want to find f of 1. Well, f of 1 means plug in 1 for x. If I plug in 1 for x, f of x is equal to 5. Okay. If f of x equals 0, let's find that. F of x equals 0, that's right here. Then x equals 6. That's not too bad. F inverse of 5. So what we want to do is undo the function f, but we want to start with a value of 5 over here. So we start with a value of 5 and then we undo it. That gives us to an x value of 1. Let me show you another way of saying this. We know that f of 1 is equal to 5. So if I want to undo that function, I'll have to take the inverse of both sides. I'll get 1 is equal to f inverse of 5. Finally, we have if f inverse of x is equal to 6, then x equals. I'm going to use the last example because I think it's going to help us through this one. F inverse of 5 said start in the f of x column, go back to x. So if f inverse of x is equal to 6, so I'm starting in this column, I need to figure out what x value to pull from here, but I know that I'm going to get 6 out. When I look at the value of this column, I'm going to get a 6 out, so I'm going to get 0. Let me write it like I did this last one. I know that f of 6 is equal to 0. What that means is f inverse of 0 is equal to 6. Well, that's what I wanted. I wanted the x value such that f inverse of that x value is equal to 6. That gives me 0. It takes a little bit of practice to be able to know when do you start here, when do you start here. But keep trying them and you'll start to get it. It just takes practice. The last thing we're going to do is find our own inverse functions. So if we are given a function and told to find the inverse, first thing we want to do is rewrite it. So instead of saying f of x or g of x or p of x or whatever it is, we want to rewrite that function notation as y. Then we're going to switch the x and the y. Because remember how when we were doing the graphs, we were able to switch the x and y coordinates because we were symmetric over the line y equals x? That's why we're going to do it here. Then we're going to solve for y, and finally we're going to replace y with the inverse function notation. A lot of my students tend to like these. They think they're fun, so I'm hoping you guys will enjoy them as well. First up, we have f of x equals 5x plus 8. First thing I want to do is instead of writing f of x, I want to use y. Then I do my switch. Y is now x. X is now y. Then I want to solve for y. I want to get the y by itself. So I need to subtract the 8. I get x minus 8 over 5 is equal to y. So I subtract the 8 over and I divide by 5. I get x minus 8 over 5 equals y. Finally, I need to do my inverse notation. So instead of y, this is going to be f inverse of x. It's f inverse because I switched the x and the y. So it's not f of x back. I switched the x and the y, so now it's f inverse of x. So f inverse of x is equal to x minus 8 over 5. You can always check your answer by finding f of f inverse of x and by finding f inverse of f of x. So like we did in the first couple slides where we were checking to see if they were inverses, you can still do that. Next up, we have g of x is equal to the cubed root of x plus 9. So I'll start by switching that g of x for a y so that I'm not in function notation anymore. And we'll have y is equal to the cubed root of x plus 9. Then I do my switcheroo. X is equal to the cubed root of y plus 9. And now I need to get that y alone. Right now it's under a cubed root. To undo a cubed root, I'm going to have to cube both sides. Kind of like how if it was under a square root, I could square both sides. It's under a cubed root, so I'm going to cube both sides. That's going to give me x cubed is equal to, the cube and the cube root undo each other, and I'm left with y plus 9. Then I can subtract the 9 over, and we get x cubed minus 9 is equal to y. And finally, we use our inverse notation, inverse function notation. So we have x cubed minus 9 is equal to g inverse of x. So g inverse of x is equal to x cubed minus 9. Next up, we're looking at h of x. It's equal to 15 over x plus 7. I start by replacing that h of x with a y. So we get y equals 15 over x plus 7. We do our switcheroo. X is equal to 15 over y plus 7. Then I need to get the y by itself. This one's going to be a little bit trickier than some of the others, because right now my y is in a denominator. What I'm going to remember is if I have a fraction equal something, I can put that something over 1 and then cross multiply. That'll give me x times y plus 7 is equal to 1 times 15, which is 15. That gives me xy plus 7x is equal to 15. And remember, I'm trying to get the y by itself. So I can subtract the 7x over, and I get xy is equal to 15 minus 7x. And then to get the y completely by itself, I divide both sides by x. I get y is equal to 15 minus x over x. Then I need to go back to my function notation. So this one was h of x, so this will be h inverse of x is equal to 15 minus 7x over x. So h inverse of x is equal to 15 minus 7x over x. I would like to point out one thing that could have made this easier. If you notice it, great. If you don't, it's not a big deal. We had x times y plus 7 is equal to 15. And I was trying to get the y alone. Well, this is x times something. So right now, I can divide both sides by x. And I'll be left with y plus 7 is equal to 15 over x. To get the y alone, I just move the 7 over. Y is equal to 15x minus 7. And then I go back to my inverse notation. H inverse of x is equal to 15 over x minus 7. This means the same thing as what I got before, because if you break up the fraction, that's how it simplifies. Either one is perfectly acceptable. Whichever one you like better, go for it. Finally, we have j of x, and j of x is equal to 9x cubed minus 7. I'm going to start switching my j of x out for a y. That gives us y is equal to 9x cubed minus 7. I do my switcheroo. X is equal to 9y cubed minus 7. I'm trying to get the y alone, so I'll add the 7 over. So x plus 7 is equal to 9y cubed. I can divide both sides by 9, and x plus 7 over 9 is equal to y cubed. And to get the y completely alone, I need to take the cubed root of both sides. So I will get the cubed root of x plus 7 over 9 is equal to y. And then I just need to put it in my inverse function notation. J inverse of x is equal to the cubed root of x plus 7 over 9. So J inverse of x is equal to the cube root of, that's a cube root of x plus 7 over 9. So for finding inverse functions, we have our sets of steps. We do them the same way every time, even though they might look a little different as we're solving them. And again, if you want to check your inverse, you just need to find the composition of the function with its inverse, f of f inverse of x, and f inverse of f of x, so on and so forth.